Just kick it right off and extra practice problems. And again, like we do during our reviews, are there any particular questions that you know of right now you'd like to give me the number of to make sure we can review those during this class period? If not, we'll just start at the top and go down. Yes, Gino? Number 7, okay. And number 7 is a structure, okay. Now, there were several of you that had difficulty on the structures yesterday, and some of the structures I marked as being correct. They are, you've got the appropriate bonds in the right places, but the way you're drawing them is kind of unstandardized. So we'll talk about that a little bit today, too, just to help you, because, I may give you credit for it, but for another chemistry teacher, or especially as we move forward, you start to not only have the bonds right, but indicate them right in the molecule. It'll be important in the next module when we're doing geometries that you have a nice clean structure to start from, because the next module builds from your ability to draw a good Lewis structure of a molecule. All right, so draw the Lewis structures for the following atoms. This is number 1, obviously. Lewis structures for SR, KR, S, and BI. Okay, thank you, Lexi. What's the easiest way to figure out how many valence electrons we're going to have if we have a periodic table available? What are we going to do? Okay. Let's first of all find all 4 of them on the periodic table. Help me out here because I haven't looked for them yet. Here's SR, it's 38. KR. Say again? Noble gas. Yep, there it is. Krypton. Superman. Sulfur. And down from sulfur. Right there. Okay, there we go. Okay. So let's just knock them out. SR, we read over here, it's how many valence electrons does it have? 2, okay. And so they're located at the 3 and the 6. KR, it's over there. Noble gas, so it has 8 of them, correct. All right, good tempo, which means if you don't understand, you might feel intimidated to speak up because it seems like consensus gets it. So please, if you don't, you need to let me know. Sulfur, 6. So again, if we just did it in the right order, 1, 2, 3, 4, 5, 6. Start at 3 o'clock and just keep building. Bi. How many valence electrons? 5 of them. Okay. And those are the Lewis structures for those 4 elements. No problems, right? Okay. If there are, and let's just be honest, if there are and you don't understand it, but you're too embarrassed to raise your hand, please write down the problems you don't know. Slip me a note after class and say, okay, Mr. Baker, put your name on it. Hey, I still don't understand number whatever. Let me know, okay? I know it's kind of ridiculous, but I understand the pressure, the peer pressure. So if you don't, you're nodding your head yes now, but you really don't, let me know. I'm not going to call you out unless it'd be really funny. No, I'm kidding. I'm not going to call you out. So please, I'd much rather know you're having difficulty and be able to maybe talk to you, help you. Anybody here use Hangouts or maybe Blab or anything like that? Talk to people? Have you ever heard of Blab? Okay, maybe setting up a Blab and do some like online tutoring soon. So if I can get groups of 2s and 3s to do online tutoring with me on Blab, we'll be able to do that, okay? So maybe if you get a cohort, like maybe you would feel intimidated with somebody else in the class that you know is doing better, but maybe you get one of your peers, one of your study guys, and you got about the same grade in here, so you know you're all struggling together, and you're not swift enough or not smooth enough to get somebody that's really brainy to join your study group, okay? Let me join your study group remotely, and we'll consider doing that, okay? Man, I never had anything like, of course we never had anything like that when I was in school. That was, 30-something years ago. I didn't get my first computer till I was almost out of college. And the computer I was using in college, we had the cables with the plugs, and we had to go down and do the programming by putting the wires in. So, give the chemical formulas for the following molecules. Now that I'm convinced you that I am from the Stone Age. Aluminum oxide. And another name for oxide is what? Oxide. When you see something oxide, aluminum oxide, it's aluminum rust. It's rusted aluminum, aluminum oxide. Good. B, calcium sulfide. Beryllium carbide. And potassium nitrate. All right. Aluminum oxide. Aluminum and oxygen here and here. What kind of a molecule is it? It has one metal and one nonmetal. We're expecting it to be ionic, right? Aluminum oxide. Aluminum. What charge does the aluminum want to take on? 3 positive. And oxygen? 2 negative. Does everybody see that? That it is aluminum has 3 valence electrons, and we've designated that as a metal, so it wants to lose. Oxygen is a nonmetal, so it wants to gain. Aluminum has 3 valence, so it'll lose all 3 of them. Oxygen has 6, and it wants 8, so it needs 2, and that'll make it a 2 negative. Now, once you have this, just transpose the numbers, and Al2O3 aluminum oxide. Just as a warning to you, there's a difference between Al2O3 that's not the same thing as Al2O3. Some of you aren't using the subscripts. I've been giving you those points, but please conform that to the standard subscript. Okay? So Al subscript to O3. Calcium sulfide. We've got calcium and sulfur. Calcium, metal and nonmetal, it's ionic. What does calcium want to take on? What charge? Calcium wants to become a 2 positive. Sulfur, to become sulfide, wants to take on a 2 negative. If we simply transpose, it would be Ca2S2, but we know that they have common factors. We need to reduce that to the same proportions. So 2 to 2 becomes 1 to 1. CaS is the formula for calcium sulfide. If you did it with Lewis structures, you would see 2 available electrons in calcium and 2 addresses available in sulfur, and they would fill, and you just need 1 of each. Okay? Calcium, we need to draw it out. I saw a couple of, So let's do this. Calcium starts like this, and sulfur starts with 2 and 6. There's an available slot there and an available slot there. I'll represent these as X's. So you see calcium has 2, sulfur has 6 with 2 available addresses. We'll take one of these electrons and place it there, take the other electron and place it there, and so we'll only need 1 of each to account for all the electrons. So CaS. Beryllium carbide. Beryllium is here, and it uses carbon, right? Carbide is the ide name for carbon. Beryllium. What charge does our beryllium want to take on? 2 positive. It's a metal. Its valence is filled with a 2s2 orbital. Carbide comes from carbon. Carbon wants to 4 negative. We good so far? If we use the shortcut, we're going to transpose in subscript, so it's going to be Be4C2. Good so far on that step. Looking at the numbers, can they be reduced and keep them in the same proportion? Yes, we can. They're both even. We can reduce them again. 4 to 2 becomes 2 to 1, and the 1 is implied. So the formula is Be2C, beryllium carbide. And it's a cool thing is I found an error in their answer key, and we're right. I think. I'm pretty sure we're right. Yeah, we are right. All right, in potassium nitride. Oh, potassium. What symbol? Triangle, sure. Potassium. Charge that potassium wants to take on. 1 positive. Nitrogen. Okay, so it's 1, 2, 3, 4, 5. It's a 5A column. Nitrogen is here. So it wants to take on a 3 negative. So you transpose, it becomes K3N, potassium nitride. Okay, no questions, we'll move on. I guess I'll rephrase that. If there are no questions, we will move on. Did you all get the same answer that I did for the third one, for those of you that feel confident that it was? What did you get? Oh, okay. But other than the reduction, the multiples were the same? Okay. It adds to my confidence that I did it right if some of you got it right too. Of course, if I did it wrong and some of you got it wrong with me, we'd both be lost together. So, but I'm pretty confident that the test key here, or the answer key, is wrong in that case. Give the chemical formulas for the following molecules. Chromium-3 chloride. Chromium-3 chloride. Zinc-1 sulfide. Number 3 is titanium-4 phosphide. So if I told you a few weeks ago that you would be able to tell me what titanium-4 phosphide, what the molecular formula was, how many of you would have said, oh yeah, sure, no problem? Okay, a couple. But for the vast majority of people are like, what? Roman numerals in the middle of names? What does all that stand for? What's going on here? Well, let's prove it. Chromium-3 chloride. Where's chromium at? It's right here in the middle. We would expect these to be transitions because they're the only ones we've dealt with so far, using the Roman numerals to help us figure out what the charge, what this particular ion wants to become, because we're talking about D shell electrons. And S's and P's are fine, but remember, D's fill in a lower energy level, and so the prediction of their characteristics is a little bit different. It's a little bit more difficult for us to see. It's not as intuitive. And so they provide us with the charge by using the Roman numeral to indicate the quantity of the charge. So chromium, we look at where it's at, and we don't say what column is it in. We look up and say, well, it's chromium-3, so it wants to take on a charge of 3. It's a metal, so it's going to be a 3+ charge for that ion. And chloride comes from the chlorine. Chlorine is a 7A element, meaning it wants to have a -1 charge in its ion. In reverse and subscript, so it becomes a chromium chloride is CrCl3. Well, because the Lewis is the highest energy level, and the 4s2 and the 4p6, you're going to have, your 4 level has 8, right? But your third level is a partial shell, a partial orbital, or partially filled. And that's why it doesn't fit the standard octet rule. Okay. And that's why, quite frankly, a lot of times they figure out what these do. A lot of it comes from experimentation and figure out the characteristics because, again, it's filling a lesser energy level than the valence or the highest energy level. Zinc 1 sulfide. Where is Zn? Okay, it's over there. And sulfide, we're going to be using sulfur. Now, what is the charge that zinc wants to take on? Become a 1 positive. And sulfur, 2 negative. And so becomes Zn2S. And the last one, titanium 4 phosphide. Where is my titanium? It's right here. Titanium. We know that it wants to take on a charge of... yeah. Trying to put it in your dialect. So 4 positive from that yawning response. I heard it 4 positive. Is that right? Okay, 4 positive for titanium 4. Phosphide comes from phosphorus. Phosphorus is over here. Phosphorus is a 5A nonmetal. Transpose and subscript Ti3P4. Can that be reduced at all? No. So Ti3P4 is the molecular formula for titanium 4 phosphide. Again, speak up or forever, speak now or forever keep your peace. Here we go. No questions? Good. Order the following atoms in terms of increasing ionization potential. So, let's see, we're looking at SR, RA, and Mg. SR, RA, Mg. All right, so we have 3 elements in column 2A. The question again was, order them in order of increasing ionization potential or ionization energy. So what is the trend? If I just draw the trend arrow on my periodic table, what is the trend for ionization energy? Correct. It's from lower left to upper right, meaning if I move from left to right, they increase, and if I move from bottom to top, they increase. So if I order these in terms of increasing ionization potential, they would become Ra to Sr to Mg. So what I'm saying there is Mg, magnesium, has the highest ionization potential. Of these 3, radium has the lowest ionization potential, and between those 2 is my Sr. Okay? So in terms of increasing ionization potential, it's Ra, Sr, Mg. Okay, the next question says, which atom has the greatest desire for extra electrons? We have beryllium, bromine, calcium, and germanium. Order them in terms of increasing, or say, excuse me, it actually asks, which atom has the greatest desire for extra electrons? So which one is going to have the greatest electronegativity? Which one is out there trying to exert force to get the most? Right. So the one with the most desire is bromine. Bromine has the greatest desire. And if you think about it, metals are trying to get rid of, they have the least desire. And so least, greatest. And that trend for electronegativity is the same as ionization energy. It increases from bottom to top, and it increases from left to right. And that electronegativity, that's another way of saying desire for extra electrons. The last one says, order these in order of increasing atomic radius. Indicate for, let's say it's phosphorus, magnesium, aluminum, and argon. Atomic radius. Now, what's the trend arrow for atomic radius? Correct. Down and to the left, which means it increases as you move from top to bottom, and it increases as you move from right to left. Now, which of those two things seems to be obvious? Which direction seems to be obvious, at least to me? Going down, right? As you're going down, you're adding orbitals, you're adding energy levels. And that would seem to make sense that as you add energy levels and you add those orbitals, that the radius would increase. What's counterintuitive, which isn't necessarily what you might expect, is as you add electrons moving from left to right, you've got more electrons, but the radius is smaller. Yes, you have more negative electrons, but you also are filling within the same orbitals, and you've got a greater number of protons in the center, which draws those electrons in even more. So there are more electrons, but there are no new energy levels. You're filling already partially filled energy levels. And because the positive center is increasing along with the negative electrons, it closes the radius in. So of those three, this is the trend arrow in terms of increasing radius. Which of those four then would have the largest radius? Magnesium would. And their order would be, in terms of increasing, would be argon, which is a little bit less than, or phosphorus is greater than argon, and aluminum is greater than phosphorus, and magnesium is greater than all of them. That's the way the answer key tends to do it, putting them in that kind of, greater than, greater than, greater than. If you just put them in order from smallest to largest, just list them in order, that would be correct as well. That's fine. Any questions on atomic radius trends and applying it to the periodic table? Okay. What's the Lewis structure for NF3? Now you're going to start to get really comfortable with seeing these later because you're going to actually be using the Lewis structures and figuring out their geometries. And when you start seeing certain elements, you're automatically going to know the geometries. It's going to help you put together the Lewis structures rather quickly. I know we're not there yet, but trust me, just like you didn't know how to name a transition metal molecule a week or so ago, in a couple weeks you'll be drawing geometries for molecules and comparing one molecule's shape to another molecule's shape and starting to understand how certain compounds behave certain ways because of the geometry behind them. It doesn't mean we're not going to be using geometry in the sense of proofs and theorems and corollaries and all that kind of stuff, but we are going to be using the angle between the atoms. So it's kind of a preview for that. But now we're looking at this molecule, NF3. We've got nitrogen and fluorine. Nitrogen and fluorine. Just to make sure, are they metal, non-metal, both non-metals, or both metals? Both non-metals. Remember, we can have a metal, non-metal forms an ionic. Two non-metals form a covalent. Two metals don't form anything. So if on the exam there was a question that asked you to show how two metals form a molecule, one of the answers hopefully is this is impossible, or it's not depicted, or they don't do that, because metals don't form molecules together. They're both trying to give up electrons. So they're not going to take anybody else's electron. They're not going to share. They don't want any more. They're trying to shed. Okay? So the molecule NF3. The Lewis structure for nitrogen has 5 electrons. For fluorine, how many is it going to have? If I draw it according to pattern, it would look this way, right? Starting at 3 o'clock and building up. Now, to make it easier, I'm going to start just looking at 1 fluorine and 1 nitrogen. I know that I'm going to end up with 3 of them, and I have to use all 3, but let me just look at 1, because I can see real quickly here that if I orient my open address towards the central atom, and I know nitrogen's going to be in the center because of what? The highest number of available addresses, or the number of spaces, correct. Fluorine only has 1, nitrogen has 3, so it's going to be my hub. And if I orient an available spot, let me just go ahead and take that extra electron, and see I haven't lost or gained any electrons now. I've just oriented the diagram so that there's an open address between these two, and I'm going to assume that these two are going to share an electron because they're both nonmetals, they're covalent, they're going to do it by sharing. They're going to share, each of them are going to share 1 electron to form a shared pair. So let's look at fluorine now. We know that nitrogen's not done, but let's check the fluorine out. 1, 2, 3, 4, 5, 6, 7, 8. Fluorine has 8 valence electrons. Yes, sir, you may. You may too. So it has 8. If you notice over here, nitrogen had 5. How many does it have now that it's sharing a pair? It went from 5 to 6. Okay? And we like that trend, right? It seems to be set. Let's go ahead and do that again. If we do another fluorine, 1, 2, 3, 4, 5, 6, 7, orient the open address towards my hub molecule, or my hub atom, excuse me, and share a pair. Now this fluorine is satisfied. Let's do it one more time. 1, 2, 3, 4, 5, 6, 7. Let's share there. And now this is the Lewis structure for the molecule NF3. Okay? Let's go through and check each atom to make sure that their valence is indeed full. The octet rule is filled. 1, 2, 3, 4, 5, 6, 7, 8. So that fluorine right there is satisfied. Over here, 1, 2, 3, 4, 5, 6, 7, 8 in the shared pair. That fluorine is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. Again, fluorine sees itself as having a complete octet. The nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. The nitrogen sees itself as owning all of those electrons, and it is satisfied that it has a complete octet. So NF3, the molecule looks like this. And next module, you'll know that that's a trigonal pyramidal. It looks just like the tripod over there holding the camera, with the camera on the top being the unshared pair, and the other 3 bonds forming the 3 legs. But for this class now, it would be NF3 with those 3 single bonds, and a shared and a pair, unshared pair, left with the nitrogen. One of the encouragements for you is to not leave single electrons by themselves. When you do these molecular drawings of the Lewis structures for molecules, keep the pairs together. Bring the pairs together. Don't leave an electron in one corner and an electron in another corner, because ultimately, between sharing or ionization, they're going to form pairs. So we indicate that that's a pair, that's a pair, that's a pair, and that's a pair. All right. Lewis structure for CCl2S. Okay, so carbon, we know quickly it's got 4, chlorine, 7, and sulfur. It's a 6, so it has 2, or excuse me, it has 6, right? Yeah, 6. All right, who's going to be the hub molecule then? Or the hub atom. I keep saying molecule, but the hub atom. Carbon is going to be the hub because, okay, carbon's going to be at the hub with its 4, because it has the most number of open addresses there. We have got chlorine, and we've got 2 of them. So we've got chlorine. How many does chlorine need? It only needs one, so that's going to be accomplished with one single shared pair, right? So we know that 2 of these addresses are going to be taken up with chlorines. Let's go ahead and do that and say chlorine's going to be here. 1, 2, 3, 4, 5, 6, 7, and I'll bond it in like that. Say another chlorine, we'll put it down here. Chlorine, 1, 2, 3, 4, 5, 6, 7, like that. At least go ahead and start that way. Now we have sulfur. Sulfur's over here, and it has 6. I'm going to draw it that way for now. Because as I look at sulfur, okay, make one double bond there to start the process. We know it's going to be sharing electrons, so we've got to have at least one bond to do that. One pair. Let's count them up. 1, 2, 3, 4, 5, 6, 7. Sulfur needs one more. Carbon has 1, 2, 3, 4, 5, 6, 7. Carbon needs one more. So I'm going to bring over a single electron and orient it towards the carbon, bring one carbon over, orient it towards the sulfur, share those 2. So now we have 1, 2, 3, 4, 5, 6, 7, 8 around sulfur, 1, 2, 3, 4, 5, 6, 7, 8 around this chlorine, 1, 2, 3, 4, 5, 6, 7, 8 around this chlorine. Everybody seems happy so far. Let's check carbon. 1, 2, 3, 4, 5, 6, 7, 8. All 4 atoms have a full octet. They're looking at, they believe they have 8, and so this is the Lewis structure for that molecule. Any questions? And again, notice how it was drawn. Some of you are still putting, like, for example, let's say this carbon and the sulfur, you had an electron there and an electron there, and you were drawing this bond like this. I know what you're trying to communicate. It's not technically correct. You need to bring that bond in between the symbols. You need to bring it down here, because it's going to get very distracting when we do geometries. Okay, so bring the bond symbols within the scope of the letters, within the abbreviations. Right? And as you look around here, you should have these electrons as pairs. Technically, does this still show that you have an octet? Yes, it does, but have the electrons be in pairs. It'll help you out next chapter a lot. Right? Yes. The Lewis structure for SiS2. Silicon, Si, and sulfur. S. Now we're going to have 2 of them. So silicon over here, we know silicon because we've been talking about it a lot. It has the same basic valence structure as carbon, which is why it's sometimes thrown out there as a possibility for an alternate life form being silicon-based. So Si has 4. Sulfur is a column 6A, so sulfur has 6. I did it a little bit backwards. Let me do it standard, and then I'll rearrange it. 1, 2, 3, 4, 5, 6. Okay. Silicon's going to be in the center because it has 4 openings. Sulfur only has 2 openings. So I know that it's going to be somewhere over here. I'm going to put the other sulfur here just so I can keep. And okay. All right. Let's start building bonds. Let's look at the outside and work in. 1, 2, 3, 4, 5, 6. We need to share at least this pair. When I share that pair, how many does this sulfur now have? 7 of them. We need one more pair, right? I'm going to take this lone electron and bring it over, and take a lone electron and bring it over. And when I do that, now this sulfur sees 1, 2, 3, 4, 5, 6, 7, 8. This sulfur over here has its octet. Let's do the same thing on the other side, because if I look in the center, what does the silicon see? 1, 2, 3, 4, 5, 6. It needs 2 more. It needs 2 shared electrons. It's going to look identical to the other side. And so it's going to form like this and like this. I'm going to take this and keep my pairs together, and that is the molecule for SiS2. Questions? No. Next molecule is CS. The carbon, again 4. Sulfur, again it's 6A, so 1, 2, 3, 4, 5, 6. Because it has 6, we know right now how many bonds is it going to want to form. 2 in order to get 8. And it's only going to, the only option is to combine with this atom over here, right? So let's go ahead and just bring the second one over, because we know that we're going to need these 2 bonds to satisfy sulfur. Look at 1, 2, 3, 4, 5, 6, 7, 8. So if all we were concerned about was the sulfide ion, or excuse me, not the sulfide ion, but sulfur over here becoming octet, having its octet rule filled, or its octet, looking at it from the sulfur's perspective, it's fine, it's done, right? But we're given in the problem that the molecule is a CS molecule. If we look over to the carbon, what's carbon experiencing? 1, 2, 3, 4, 5, 6. Carbon is still there going, wait a minute, I need 2 more. Where's it got to get the 2 more from? Sulfur. We're going to bring a pair from sulfur and put them both in the middle. Because carbon can't give up anymore. It needs to get 2 more. Remember, when we bring an electron pair from sulfur and make a bond out of it, they still belong to sulfur. And they still belong, but now they also belong to carbon. Okay? So I took an electron pair from here, and I used 2 sulfur electrons to form a additional bond between the 2, because now if we count them up, it's 1, 2, 3, 4, 5, 6, 7, 8. Sulfur still has 8 because the bonds are shared. If we look at carbon now, it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 as well. And what I'm going to do is bring this over and depict it that way to keep my electron pair together. So the CS molecule has a triple bond holding them together. 2 of them are formed by a shared electron from both elements. The third of the triple bond is formed by an electron pair donated by sulfur in order to hold that molecule together and fulfill both of their octets. That's probably the trickiest one. This is the one that we mentioned yesterday that we wanted to go over, because some of you did this homework in advance and this was troublesome for you. So please make sure you understand that you can take an electron pair from one of the atoms and use it to form a bond with the other one if there's no other way to fill that octet for the other element. SBr2, sulfur and bromine. So sulfur's here, bromine's here. Sulfur dibromide. Sulfur is a 6A. 1, 2, 3, 4, 5, 6. Bromine is a 7A. 1, 2, 3, 4, 5. And I'm going to put the open slot over towards the other molecule just to make it easy for me right now. We're going to have 2 of them. Which is going to be the central atom? Sulfur, because it has 2 open addresses. Bromine only has 1, or bromine only has 1. Put the other one, for symmetry, I'm going to put the other one on the other side just because I know that I need to have 2 of them, because our formula is SBr2. And I'm going to orient the open address towards the center atom. Okay. So what I'm going to do here is I'm going to rearrange this just a bit and move that electron up there so I've got a single on both sides. Okay. Is that 1, 2, 3, 4, bromine. That's good. That fills the octet. That is your Lewis structure for SBr2. Number 12. which of the molecules in the problems 6 through 10, now you'd need to have that in front of you, obviously worked out correctly, would be hardest to break based on their Lewis structures? The CS molecule. Remember, CS, I'm not going to draw the valence electrons, but it had a triple bond. CS had a triple bond. It takes the greatest amount of energy to break up a triple bond. So if you get a question that says, which of these would be the most difficult to break, look for the highest number of bonds. If you have one molecule that clearly has the highest number of bonds, that is the most difficult to break. If you have another molecule that has a double bond in it, even if it has a double bond and a single bond, the way that this works is you're going to say that the molecule with a double bond is harder to break than a molecule within a single bond. So single, and if you've got another one like yesterday, I think it was hydrogen, it said which would be the easiest to break. And hydrogen, an H2 molecule, has a hydrogen, it looks like that. It's got one single bond holding the two hydrogens together as those homonuclear diatomics. It has a single bond. This would be the easiest to break. I think yesterday there was a center molecule, I don't remember what it was, but it had double bonds and single bonds. And so I asked the question, which would be harder to break, a molecule with doubles and singles or a molecule with only singles? We expect you to say the one with only singles is easier to break up than the one that has doubles and singles. See that? You might argue, yes, I could break the single bond in that molecule with the same amount of energy that it takes to break up this single bond, but because it has double bonds in it as well, it's considered to be harder to break up than a purely single bonded molecule.